Okay, so remember what the problem is. The problem is that your Taylor series might not give you back your function. So you're wondering, how do I know if my Taylor series works or not? Right? How do I know if my Taylor series works or not? So the question is, does my Taylor series actually recover my original function? Let's give a useful definition. We call the sum up to the nth power of the Taylor series expansion, the nth Taylor polynomial of f around A. Okay, the nth Taylor polynomial of f around A. Okay, so right, like for the sine, I'm sorry. So for for the sine function, x minus x3 over 3 factorial plus x5 over 5 factorial is the fifth Taylor polynomial around 0. Right. So here is some polynomial, right? It's not the infinite, not the power series, but you chop off the power series. You chop off the power series at the fifth degree, and that guy is your fifth Taylor polynomial. Okay. And so your question is really, oh no, let me say this. Let me introduce a notation. Let R and X be the function minus the polynomial. So where P sub n is the nth Taylor polynomial for f. Okay, so this is the remainder or the error. Okay, so coming back to, maybe I'll slow down. People are talking. Okay, so coming back to the example, right? This guy was the fifth Taylor polynomial around 0, and so if I'm talking about R sub 5, I mean the sine. You take the sine function and then you subtract off, this thing, x minus x cubed over 3 factorial plus x to the 5th over 5 factorial. Okay, and so that tells you how off you are, right? This is some approximation of the sine, and you look at the difference between the sine and your function. You say, okay, that's my error, right? That's my remainder. That's what I'm missing. Okay. What you're hoping is that as you take more and more polynomials, right? As your polynomials get longer and longer, that the error gets small, right? You're hoping, your hope is that the remainder, as n goes to infinity, the remainder goes to 0, right? That would mean that the Taylor series does recover your function. Right? That would mean that the Taylor series actually does recover your original function. Okay. But as we saw, sometimes the Taylor series doesn't recover your original function. Okay. And so what we're going to do right now is figure out a way to talk about this error and to get some control on the error and see if it does go to 0 or not. Okay. Okay. Is everyone following the story, at least? Following the idea, right? We have your function, you have your Taylor series. You're hoping that the Taylor series actually is your function, but we saw that Taylor series might not be your function. It might be some completely different function. Okay. Now, what we're saying is that, well, let's introduce this idea of a difference. We say, let R sub n be the difference between the function and the nth Taylor polynomial, right? If as n goes to infinity, that difference goes to 0, then that's good. Then the Taylor series actually does recover your function. But if not, then you can't. You don't have a Taylor series expansion for your function. Okay. Okay. So here's the theorem that's going to be really useful for us. It's called Lagrange's remainder formula. Okay, so here it is. If f has n plus 1 continuous derivatives in an interval I containing a point A, then for each x in I, there exists a point C between x and A such that the remainder at x actually equals the n plus 1th derivative, of f at C over n plus 1 factorial times x minus a to the n plus 1. I'll read it again. If f has n plus 1 continuous derivatives in an interval containing a, then for each x in that interval, there exists a point between x and a where the error equals this thing here. The error equals this thing here. So let me try to set it up. Right. So for example, right, we have over here f of x is sine x, right, and we have this Taylor series expansion, right, x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7 over 7 factorial plus minus etc. Right, that's the Taylor series around 0. Right, that's the Taylor series around 0. And what this is saying is that, so here is 0, okay? Let's choose some point x. Let's choose some point x, and this is saying that the error, so let's look at the 5th Taylor approximation. Okay, so remember this guy is called p sub 5. We call this guy p sub 5. Okay, and we're wondering, how bad is p sub 5? Okay, and this thing tells it to us, right? How bad is p sub 5? The n r sub 5 has to equal the nth derivative, the 6th derivative evaluated at some point c over 6 factorial times x minus 0 to the n. For some c between 0 and x. Okay. Right. Remember the 6, I think the 6th derivative, 2 is going to be, what, negative sine. So negative sine c. Okay, so this tells you exactly what the error is going to look like. Anqing?
But there is not 6.
Why is there what?
Is not 6.
Why is n not 6? Oh, it should be 6. N should be 6. 5 actually. Oh, 6. Okay. So this tells you what the error looks like. In fact, you can get some. So for example, let's make this even more concrete. Okay. Suppose you wanted to know the sine of. Suppose you wanted to know the sine of pi over 100. Okay. Somebody said, "What's the sine over 100? Sine of pi over 100?" And you'd say, "Well, I don't know. But I'm going to take my 5th Taylor approximation, right? I know that it's something like pi over 100 minus pi over 100 cubed over 3 factorial plus pi over 100 over to the 5th over 5 factorial." Okay, right? That's what the 5th Taylor polynomial says. Okay, and you could say that's going to be my guess, and then I can even tell you about how wrong I am. Okay, I know that the error equals negative sine of pi over 100 over 6 factorial times pi over 100 to the 6th power. Okay. There's something a little bit bad about that, right? What's bad about that? I don't know what sine of pi over 100 is, right? I don't know what sine of pi over 100 is. Okay, but at least I'm gonna be a little reckless here. I'll say at least I know that the sine, whatever it is smaller than 1, right? The absolute value of the sine is smaller than 1, right? So I know that this is smaller than pi to the 6 over 100 to the 6. Okay, so I can even tell you that at the worst, I'm this far off, and that's actually really, really close. Right? I've got 100 to the 6th power on the bottom. Right, so this is actually a very, very good approximation. Okay, so you see how knowing the error is useful, right? So you make your approximation, and in fact the error is pretty small. Okay. Is that making sense? Making sense? Okay, so I'd like you to try something, which is I'll give you a problem. Figure out e to the 1/2 within 0.01. Okay. I'd like you to figure out e to the 1/2 within 0.01. Okay, that's the problem. Try it. You have enough information that you should be able to answer this. So maybe I should say, using the expansion around 0. So using e to the x's expansion around 0. Okay, talk with somebody nearby and say what you're doing if you're still awake. Okay, let's try it. Okay, so first off, what's the expansion around 0 for e to the x? Who can tell me that? First off, the Taylor series expansion is what? X to the n over n factorial, right? And then equals 0 to infinity. Okay, so that's your Taylor expansion, right? And so the first thing we should probably figure out is how far out do we want to go, right? Like how many, right? This is 1 plus x squared over 2 plus x cubed over 3 factorial plus blah, 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 right? And we're trying to get some approximation of it. We should figure out how far we need to, where we're going to stop, right? We don't want to sum the whole thing, okay? So how far do we need to go? How far do we need to go? Well, we want the error to be smaller than 0.01, right? So we want r sub n at 1/2 to be smaller than 0.01, right? We want the error at that point to be smaller than 0.01. Okay. Okay. I actually messed up something here, back here. I'll fix it in a second. Okay. So we know that Rn at 1/2 equals e to the c, right? E to the c over n plus 1 factorial times 1/2 to the n plus 1. Right? For some c between, for some c in 0, 1/2. You see, that's actually, I messed that up here. This should have been sine of c, right? For some c between 0 and pi over 100. Right? This should have been sine of c, which I don't know, but I know it's smaller than 1. Okay? Okay. So, okay, so we want what n should we choose? What n should we choose to make this smaller than 0.01? Well, we just need to figure it out, right? Let's just make up something. Right? We know that you see what's happening, right? If we take if we take n to be 10, say, if we take n to be 9, right? Then this is definitely going to be good enough, right? So just we want this thing to be smaller than 0.01, so this thing to be more than 100. What? 3? What 3 do? 4? Let's say 4. Okay. I'm going to take n to be 4. Let's take n equal to 4. Because then e to the c over 5 factorial times 1/2 to the 5, right? You get 5 factorial is what, like 120, right? So you get 120 and you get 32. Actually, this is more than we need. This is smaller than e to the 1 over this, right? So this is certainly, actually this is much better than we need. Probably I could take n to be 3 or 2. Yeah, do you guys see what I'm doing? Everybody see what I'm doing? Does everybody understand what I'm doing? No? Okay. Yeah. What do you not understand? Well, can you?
Because,
Yeah.
the e 1/2
Mhm.
over x inherit plugging that one.
What is this? Okay, let me say it like this. Okay, so e to the half is some number, okay? And in fact, e to the half is going to be 1 plus 1/2 plus 1/2 squared over 2 factorial plus 1/2 cubed over 3 factorial plus blah, 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 to the end of the series.
I didn't get this one because for the others you use is it contains x, but for this one it's a number. So how you get the equation?
Remember, so over here, right, we have the sine function.
Yeah, that's a
And
function.
the sine of x is x minus x cubed over 3 plus 3 factorial x to the 5th over 5 factorial, blah, blah, blah. And then we said, suppose we're looking for a sine of pi over 100. Then we take pi over 100 and plug it into this thing. Right? Right? Sine of x is this infinite series, right? Sine of pi over 100 is going to be just evaluate that series at pi over 100. Same thing here. E to the x is this infinite series. If I'm trying to figure out e to the 1/2, well, I'm just going to put in 1/2 into this thing. Okay, I put in 1/2, and my question is only how far out do I want to go to get something that's within 0.01 of the actual answer. Okay, and what we're doing over here is saying that if I go up to n equals 4, right? If I take 1 plus 1/2 plus 1/2 squared over 2 factorial plus 1/2 over 1/2 cubed over 3 factorial plus 1/2 to the 4 over 4 factorial, then actually that is going to be very, very, very close, very, very close to the actual answer. Okay, it will be, this much off. It will be at most this much off, which is very tiny.
No, you just choose random x to represent the e, because how you can see the right side is very, very close to that e.
So,
Because you just e is just a random number, it doesn't represent that number.
So e to the 1/2 actually turns out to be this infinite series. Okay.
You can choose any number turns out to be that, right? Because for that function you get it's just x, it's not e.
Right. So certainly, if somebody asked me for e to the 4th, then I would have put in x equals 1/4 here. If I chose some other number, if I said e squared, I would have put in a 2 here. Right? But the question was to figure out e to the 1/2. Right? Let's figure out e to the 1/2. E to the 1/2 turns out to be this infinite series. And the question is, we wanted to figure it out within 0.01 And we say, okay, if we go out to here and stop, that actually will be within 0.01. Okay. Right. So this is the point. The remainder formula, right? The remainder formula tells you how far out you need to go. Right. Tells you how far out you need to go. Okay. Does this make sense? Anybody else? Is this making sense for everybody, or are you? Is anybody else confused? Okay. Okay. So yeah. So if you if you calculate this, I bet even the third term, or even up to here or to here, would probably be good enough. Let me get back to the original question. Okay, remember what the original question is, right? The original question is, how do you know if your Taylor series gives you back your original function? Okay, how do you know if your Taylor series gives you back your original function? Okay, and let me show you. Let me show you how the remainder formula gives that to you. Okay, so. How do we know, so getting back to the original question, how do we know that the Taylor series recovers f? How do you know that the Taylor series recovers f? Let me give an example. E to the x. Okay. E to the x. How do we know? In fact, x to the n over n factorial, n from 0 to infinity, actually recovers e to the x everywhere for all x. Okay, but let's see how that works. So, why? Okay. Well, the Lagrange remainder Lagrange remainder formula says that Rnx is smaller than absolute value of e to the c over n plus 1 factorial times x to the n plus 1. Right? It says that for any x, the error is this small. Right? Right? It says that the error actually equals e to the c over n plus 1 factorial times x to the n, times x to the n plus 1. Right? And so I'm going to take absolute values, right? I'm going to take absolute values. Okay. This thing is smaller than this thing here. Okay.